So, good morning, everybody. So, I'll be talking about machine learning, and specifically, I'll be talking about how to conduct agile experiments with machine learning and how I used F# to this. So, first, quickly, my name is Matthias Brandewinder. You can find me on Twitter. My two big interests are on one side F# and functional programming, and on the other side machine learning. I live in San Francisco, which you probably got from my accent. So the accent is obviously not from California, but I'm French. I just moved over there. It was sunny, and so I stayed. So where is this talk coming from? So a couple of months ago, I did a machine learning competition on Kaggle. And usually when I do machine learning, I tend to work alone. And this thing was a bit different for me because I decided to team up with a couple of friends. And so we ended up with a team of 7 people. All of them are good friends. They're all very good software engineers. And so we started coding. Everything was fine. And within a couple of weeks, even though everybody knew what they were doing and everybody was competent, we had a repository, and the repository was a complete mess. We had like scripts everywhere, like 30 scripts. Half of them were not working. And so that got me thinking, because why is it that even though we put competent people together, within a couple of weeks, we would get code together which looked like a complete shame. And so that begs some questions, so that got me thinking. And so a couple of thoughts on this was, perhaps we were bad, but like the other train of thoughts were maybe if we work as a team, so when you work as a team, this is when you start to see if you have a problem as a process. If I'm coding alone, there is no need for a process. I do whatever I want. That's all fine. When you start to put people together, this is when you need to start to have a bit of discipline. And so it got me thinking about what is it maybe about machine learning, and what would be a good process for conducting a team effort with a machine learning team. So that's one thread in this talk. The other one was like, if I want to think about the process, perhaps I need to think about what makes machine learning different from writing regular code. So that got me thinking as well, and that's another thing I wanted to explore. And finally, on a completely different direction, I do realize that most people in the machine learning field tend to use dynamic languages, like maybe Python, maybe R, all these things. I've been using F# with great happiness for the past 3 or 4 years doing that. And so I thought it was maybe interesting too to explain why we picked that language and what works about it. So this is kind of what I'm trying to do with this talk. Also, unfortunately, I don't have the silver bullet on what it means to do machine learning right with a team with F#. This is more like thoughts, work in progress, so I'm going just to share what I found so far. All the code for this is also on GitHub, repositories like James S. Dixon, Kaggle Home Depot, so if you want, you can see it. You have the good, the bad, the ugly, like this is what we did. So this is how I'm going to approach the problem. Like first, if I want to talk about, so the first thing I should do is probably introduce what is it that we are trying to do. So I'm going to talk a bit about the competition itself, like the problem we are trying to solve. Then I'm going to discuss maybe agility, like how we approach this, so that we went into a mode where we could actually iterate fast, produce models in a good way. And then I will discuss another thing, which is pre-processing of data, which was another problem we encountered, and then there's like a couple of parting thoughts. So what was the problem about? So this was a Kaggle competition. If you're not familiar with Kaggle, it's this place where you can go, they have data sets, they have competitions. You have a data set, you don't have machine learning people, you put it on Kaggle, people try models, and the best model wins. This particular competition was about Home Depot. So Home Depot is I don't know if you have Home Depot in Spain, but Home Depot is the place where you go if you want to buy a saw, if you want to buy a hammer, if you want to buy paint, if you want to buy toilets, showers. So this is, Home Depot is a store. And because it's the 21st century, Home Depot has a website. They do. And if you go to the website, you will find a page like this where you have a big box in the middle, and here you type like what is it that you want, and you will type I want a hammer, and hopefully you will get a recommendation for the best hammer you can buy at Home Depot. So that's the back of it. And I just wanted to mention also the team members, because this is just not me, but a bunch of people. So we were 7, and the 2 people I want to mention is Jamie Dixon and Taylor Wood, because they were heavy contributors on the project. So just pay respect to my team members. And also
so unfortunately we didn't win, so that happens, but like we did pretty decent. So in the end, like the competition, you could win $40,000. We didn't make any money. Whenever you have money in competitions, the competitions get very intense. So there were like over 2,000 teams, and we ended up ranking 122. That's top 6%, which I think is pretty okay. For the anecdote, at some point we actually ranked under 5%, which was my goal. But then what happened was people cheated, which is very bad. And people cheated, and the unfortunate part about this is like people cheated, and so they were eliminated from the rankings. And as a result, is like we started to go down and down and down in the rankings, and so we went from 5% to 6%, which is kind of sad because we did everything right. Other people cheated, and in the end, is like my position went down. Like this is completely unfair, but this is how our life goes. So to go back to the problem, like I presented initially the website with the search box. So the point of the competition was this. Like if I go to the search box and I type something like I want a 6-inch damper, whatever that means, what will come up on the website is a long list of products. Like for instance, I could have something like a Batik door energy conservation products premium 6-inch backdraft damper. Why not? And the question here is what came back from the website, or is the recommendation any good? Like is this what the person wanted or didn't want? So the data we had to answer that question looked along these lines, because it's because like every project ends up involving CSV files. We had like a gigantic CSV file, and in a nutshell, the CSV file looks along these lines. What you have is like what the person asked. I want an L bracket. What the person received: a Simpson strong tie 12 gauge angle, under rating between 1 and 3. 1 would be, this is terrible, this has nothing to do with what I wanted. 3 is exactly what I want, and 2 is like, it's not too bad, but it's not too good. So given that statement, like the problem we were trying to solve is really this. If you give me a search, which is going to be a string, if you give me back a product, which is going to be a couple of strings, like the product description and all of this, I'm going to try to predict if that recommendation was relevant, relevant being a number between 1 and 3. 1 is awful, 3 is excellent. The competition itself, we had like 70,000 training examples, like 17 examples of queries and results and ratings. We were trying to predict 20,000 searches and products where we don't have the rating. And the goal, the ranking on the competition was on the root mean square error, essentially like how far off you are from the number you're trying to predict. And we had 3 months to be the best team. So we were not the best team, but we did decent. So I mentioned like this is a machine learning competition, so I should probably talk a bit about machine learning now. Before starting with machine learning, I will take a different hat, which is my software engineering hat. And so in the end, what I'm trying to do is this, is like I have an observation, which is going to be, so this is like F# code. An observation is going to be 2 things essentially, a search string, a product string, and I'm trying to give you a function back, which is going to take an observation and give you back a number between 1 and 3. So there is a completely trivial implementation which satisfies all the criteria. I could give you a model right now, which is a predict function. That predict function will take an observation, and why not? I'm going to return 2 every single time. And so this is, from a software engineering perspective, this is completely correct, right? It's like the code is flawless. I can unit test it to death. There is nothing blatantly wrong about it. So you could say at that point, okay, ship it, we're done. And so I'm suspecting that when you are seeing this, is like your reaction should be, that can't be right. And that's not right. So obviously it's not right. So I have code here. But what I'm trying to achieve is, the reason I'm pointing this out is like because if I take my software engineering hat, I'm kind of missing the boat here. One is like compared to most software engineering activities, here is that my domain is entirely trivial. It's like 2 strings, 1 float, finished. So it's like the problem is not with modeling the domain. The other one is like, sure, I can write a unit test checking that my function is always giving me a 2 back. That's, I can test it, and that's completely, I think I lost the microphone, is that right? Can people hear me? Yeah, okay. Then it's like I will keep going like that. So I could write tests, but that would be entirely useless. And really, in the end, whether my code is correct or not correct is not really relevant here. So these are really important criteria normally in software. None of them is useful for my problem. So the question is like, what is it that we're trying to do here? How is a machine learning problem different from writing a regular business application? And so if you take the typical process of a machine learning person, is like what we will do in this competition is something along these lines. Like we have one function predict, which is trying to take an observation and predict, and we will take that function and change it over and over and over and over again. Essentially for 3 months straight, that's all we do. And what we're trying to do here is like we're trying to be creative, and what we're trying to do is not something which is correct in the sense of unit tests, but something which is good in the sense of fitting the data right or giving me answers which are close to what I want to see. And that's a very different goal from what you typically do with software. So a couple of observations is like where normally you have a bunch of features in an application. Here I really have one single feature, which is my prediction function. The second point is like in most applications, like you have test, and at some point it's complete, all the tests pass, and you ship it. Here, that's not going to be the case. Unless I'm extremely lucky, I will never get a perfect prediction function, and so I will never really be technically done with my problem. The other thing which is interesting is like normally when I write an application is you have one block, finish it, one block, finish it, one block, finish it, put it all together, ship it. Here, I might have actually many features or many versions of my code which I'm going to try in parallel because I'm trying to really run experiments and compare, is this predict function better than this predict function or than this predict function? So instead of like a master trunk where I have my code which is evolving in linear fashion, I might have like many different versions of my code living at the same time, and I'm really trying to decide by experiments which one is the right one. And finally, like there is no correct model. It's like if I think it's good, it might be good, it might not be good. Like the only truth here is like am I better at making predictions? So that's kind of what we're trying to do. And so now I'm going to move. So part of the point here is like I'm trying to point out at all the ways writing machine learning code is different from writing normal code. Even though it's about code, it's a bit different. And so the question here is like, or the point here was maybe that's explaining why we had problems. Because if you take your software engineering hat and try to approach machine learning the same way, chances are, because you're doing things which are different, the process which works for one will not work for the other one. And so what is it that we should do about the process? So one word I used in the previous slide was we're trying to conduct experiments. And so in that frame, I started to think maybe instead of looking into software, I should look into different areas to figure out better ideas or better ways to do what I'm trying to do. And so if you take the word experiments, that's really coming not from software engineering, but that's coming from science. And so my question was like maybe we should look at what scientists do. So I'm going to do gross simplifications on what science is about, but like let's explore for a minute what a scientist does. And so what a scientist does is like first you start with a question. You care about something. Maybe I care about whether the moon will be full tomorrow. Maybe I care about how fast that rock will fall. Like I have something in the world, a phenomenon which I care about explaining or predicting. So what I really want to do here is, as a scientist, I want to do something along these lines. I have an observation. Maybe today the moon is full, or maybe I have a rock which is 27 kilograms. I'm going to put it in a model, and that model is going to give me a prediction. That's actually a slight simplification. What the scientist really means, or what we really mean as a scientist, is something along these lines. I have observations which are the world. I have predictions, but what I'm trying to do is I'm trying to take an observation. I'm trying to extract numbers out of this, which would be features. So in this case, my rock is maybe 23 kilograms. Maybe it's like 57 centimeters wide. So all things which are like out of the rock, I want to reduce it to a couple of numbers. What I mean by a model is really a function. I want to pass all this vector of inputs into a function so that I get a value y, which is the thing I'm predicting. So this is what we mean by a model. So, so really the first step is like take all of this and formulate a model. I have this vector of input. I'm trying to find a function which will predict how things behave. For instance, I have two models of the world. One of them would be planets are describing circles which are around the sun, and planets describe circles which are around the Earth. So one of them is obviously much more wrong than the other. But this is what we're trying to say is like the world looks like math. This is what we mean. So how do we move from here? Now that we have a model formulated, what we're trying to do is that we have observations with results. We saw that in the past, if I dropped a rock, it took 23 seconds. If I dropped a rock, it took 12 seconds. So I have a long set of observations and results, which are like a ground truth. And my next step will be to calibrate my model. So I think the world behaves that way. I think my function has this shape. I'm going to put the data in the model, and I'm going to try to find the parameters which fit the best, so that given my hypothesis, this is the best model I could possibly get. So at that point, I have a model, and maybe I'm happy, and I'm actually not completely finished. because at that point, all I have is that given the data, I have something which fits, but in the end, what I'm trying to do is to produce predictions about the future. And so this is a quote I really like from Niels Bohr. Niels Bohr allegedly said, like, prediction is very difficult, especially if it's about the future. Which is correct. And which is also like, so the whole point is not to find something which fits the past. What we're really trying to do is like, does this fit with what will happen in the future? Also for the anecdote, so you can probably not read it, but like this is coming from Wikipedia. And there is a little caption on the picture here, which I just love. So the caption says, "This is a photograph showing the head and shoulders of a man in a suit and a tie." And so this is again, like this is something which is entirely correct and entirely useless. Like this is I really love this caption. So anyway, so what we're trying to do is we're trying to predict the future. And so the next step here will be like, I think the right model is this. I have a model calibrated, and the proof of the pudding will be, I will make a bold prediction and say that tomorrow the moon will be full. And if the moon is full, my model is not wrong. If the moon is not full, I know for sure that my model is incorrect, and I have to go back, try a different formulation, and iterate. If it's validated, then my model is okay, and I move on, and I'm happy with my life. So this is, in a nutshell, like the overall process. Like what we have is really 3 steps. Is like one of them is like I have facts or observations. I'm going to formulate a model, which is like a vectors function output. I'm going to calibrate the model, which is like given the model I think is right and given the data I have, like try to find the best fit. And then I'm going to validate the model, looking at data which I didn't use for my model to see if yes or no it's plausible. And as it turns out, this is pretty much like what machine learning people do. Like what was a physical experiment is also what people do in machine learning. They conduct experiments in code. My first step will be, I will formulate a model. So that would be called like features extraction in the machine learning world, like observation, this is the numbers which matter. I'm going to do calibration. So in the machine learning side, this is what people would call learning, but that's exactly the same thing. I'm fitting a model to data. And finally, I'm going to validate, and this is where like the 2 worlds use the same vocabulary. Very briefly, on the modeling side, is like what you're trying to do is like take an observation, make it into a vector. So for instance, on the Kaggle, like on the Home Depot problem, is like what we're trying to do is we have observations which are 2 strings. So we could start extracting numbers like how long is the search string, how many words do we have, all sorts of things. So we're trying to transform strings into vectors. And what we try to do is to learn a function f, such that if I give a vector to f, I'm going to get something which is as close as possible to the relevance. The learning part is where people get all excited and talk about algorithms and which one you should use. In the end, is like I think it's kind of overrated. Like an algorithm is just an optimization procedure. You give it data, and it's going to find the best fit. Depending on the data you have, you will take one algorithm, the other one. Like, but this is not, in my opinion, the most important part. And the validation part is, so this is where it's convenient to be born in the 21st century, or 20th century for me, and not in the Middle Ages where you had to do observations by hand. Like instead of, one thing I could do is like build a model, ship it in production, see if it works and come back, like wait for true data. If I have actually a lot of data, I can do something much simpler, which is I can take my whole data set, take half of it for learning, half of it for validation, and that way I can use data which my model has not seen, and I can check if yes or no it's plausible that it works. So this is a much more comfortable place to be in. So a recap is like a recap here is like machine learning is like somewhat different from writing standard regular business applications. In traditional software, what you're really doing is like building incrementally, block by block, a solution to complete discrete features. Here in machine learning, we're doing something different. We have one feature, and we're going to create many experiments trying to improve a predictor. And so the normal process, everything you're using normally is probably not going to work great. So this was a bit of the theory. Let's take a look a bit at the practice and how people make the sausage, or like what's happening and when people do machine learning in practice. So in practice, based on what I described before, most people would use something like a script, and pretty much like every script I have seen looks more or less this way. It's like you're going to have 4 steps. It's like one is like you obviously need data, so you're going to have like load data. Second one is like out of that data, you're going to try to extract features. So out of that data, I want numbers, I want vectors. Then is like you're going to pick one of the many algorithms you could use, plug the data in, learn, and finally you're going to validate by running that model against another set of data to see if yes or no it's any good. That's kind of how every script I have seen looks. Doesn't really depend on what language you use. And so now I'm going to take that and show you like how the initial scripts we had looked on the F# side. And I want to discuss that. So let's go here. So here we go. So first is like what I'm starting with is like I have my CSV file, and my CSV file is more or less what I described. It's like a long list of like search strings, resulting strings, and ratings. So this is what I'm going to use. And what I need is I need to put this into a model, which is going to be an F# script. So let's do that right now. So my first take at the model, I will start with something simple, and maybe to explain how good or how bad the recommendation was, I can use a couple of simple metrics, maybe how long the search was, maybe how long the description was, maybe some other things. So I'm going to start with something simple first. First step, loading the data. So that's not too hard. So this is where like actually F# shines, because we have like this feature called the type provider. And so with the type provider here, what I can do is I can simply say, hey, like here is a CSV file, look at it and create types for me and load the data in memory. And so I'm going to just do that right now and I'm finished. So that's I'm happy because I don't have to deal with that part, which is usually pretty annoying. So I have data. Next step is like from the data, I want to extract features. So how would that typically look? So I need really two things to do some learning. Is like I will need both the input, like what are the values which go into my vector, and what is the output, meaning like the number between 1 and 3, which represents how good or bad it was. And so in this case, this is how it would look like. What I'm going to say, I'm going to take my sample, which is like the data I got from my CSV file. And then for each of the rows here, I'm going to extract two things. The first thing I'm going to do is I'm going to extract the relevance, like number between 1 and 3. This is what I want to predict. This is going to be my output. And then is like I want to extract a bunch of numbers which are going to be my features. And so in this case, these are not particularly smart features, but I have to start somewhere. So I'm going to say, for instance, that let's take how long the search term was, and let's take how long the product description was, and then make it into an array and unzip this. So let's do that. And now if I do that, is like what I'm going to get here is like a magnificent list, a magnificent array of numbers, so like not particularly exciting, but I extracted my data and I have features. So next step, this is good. Next step is I need to plug it in an algorithm to do some form of learning. So again, doesn't really matter which one I use, I have to start somewhere. So I'm going to start with one of the simplest possible one, which is a logistic regression. And so this is where things start to get a bit earlier, because now, depending on the algorithm you use, the algorithm might expect the output to be in different forms. In the case of the logistic regression, the outputs are expected to be somewhere between 0 and 1. I have numbers between 1 and 3. That's really not going to work great, so I need to do a bit of reshaping of the data. So here, first, I'm going to take my output. And instead of taking the output between 1 and 3, I'm going to renormalize it to put it back all between 0 and 1. And to get normalized outputs. So now I should be in a better shape. And now I'm just going to prepare my logistic regression, and I'm going to just launch a bit on learning. So hop, let's do that. And I'm going to learn. So now let's the thing learn, like it's doing its thing, and it's done. And now I have a model which is possibly a good fit, possibly a bad fit. So now we need to check that. I'm going to do that in a quick and dirty way. I'm not even going to do a separate validation set. I'm just going to run it on the full training set. So here what I'm going to do again is I want to take every prediction, every observation I have. I want to extract the features. I want to plug it in the model, product the output, and check is this close or is this far away from what I'm trying to predict. So take an observation, extract the same features as before, search term and product title, pass it to the regression, and renormalize it because now the output is on 0 and 1. I want to be on 1 and 3, so pop, reboost it into the other scale. And now I can compute like how good or how bad it is. So I'm just going to do the RMSE by computing like on average how far off is the prediction. And so if I run this, I'm going to get a number. That number is 1.48. Given that my scale is between 1 and 3, that model is probably the worst I could possibly get. Like it means like on average I'm off by 1.5 on something which is on a scale of 3. So like this is pretty awful. But that's fine. So why did I want to show this? So the first thing to note is like scripts are nice. F# is nice, like in 80 lines of code, I got a full script which is describing my whole model, doing all of this. So this is the good side. The bad side is like I have a model which is not really working. Like the predictions are just terrible. So now is like I want to improve that model. And so if I want to improve that model, I can do a couple of things. like the first thing I could do is I could add, remove, or edit features. Like maybe like the features I picked are not very good, so maybe I want to measure how many words I have, if I have capital letters, whatever. I could also take something different from a logistic regression, like whatever you like, support vector machine, anything. And so I will want to start to modify my script. And so now again, if you go back from the machine learning side and back to the software engineering side, this is where you can start to see how this is going to go very poorly. Because if I want to do this, my script has a code duplication literally everywhere. Like if I want to modify a feature, I will have to modify it in two places. Like I have to modify it here, because this is where I extracted things out. And now I also have to extract it in the other place where I was trying to make my prediction. So now it's like you can see already how with 7 people working on this script, it's like bugs are waiting to happen, like it's almost a given that you will have problems. The other place where it's going to hurt is like if I'm trying to use maybe something which is not a logistic regression, I will also have to change things like this. Like here, I'm normalizing data in this place, and I'm denormalizing it in the other place where I'm making predictions. So again, I have code duplication. It's going to be painful to change, waiting for bugs to happen. So this is not going to be very good. And this is kind of, I think, why we ended up with like a nightmare of a repository within 2 or 3 weeks. This is exactly what fell on us. So we cannot really work easily with features at that point. It's it's not easy to swap algorithms. That's not good either. And even if you go a bit further, it's very hard if you look at the script to see what the features are. It's like you have to go deep in the code to see where I'm extracting things inside an array, and that's a bit of a problem. I'm a big fan of domain-driven design in general, and in domain-driven design you have this idea of a ubiquitous language, and the idea of the ubiquitous language is like if I have a problem and I talk to a domain expert, the code I write should look close to the way people talk about the problem. And now it's like if I look at this script, it's like what I told you I was trying to do was I was trying to do an experiment, extracting features, learning, all of this, and I see none of these words anywhere in the script. So this is a bit of a problem, right? It means like I'm writing code right now, which is working, that's the good side, but which is absolutely not close to the way I'm thinking about the problem. And so, so maybe we should change that. So I'm going to show you a bit what we did to change this. So yeah, the problems are, one is like it's very difficult to keep track of what the features are and how they work. It's hard to swap algorithms, and I'm also going to repeat a lot of dumb work across different scripts to load data, to do all these things, and the code is not really representing what is it that I'm trying to do. So this is very wasteful. So definition of wasteful would be like I'm spending resources, I don't have much time, I have a small team, I'm trying to achieve something and I'm spending a lot of energy on the things which don't matter, and I'm not in a position where I can do easily what I really want to do. That's a waste. And so if you're in a place where you have waste in a process, what you're trying to do typically is to do two things. Is like you want to build flexibility in the places where you're going to have a lot of volatility or a lot of change. In this case, for instance, features. I would want to be in a place where it's easy to change the features, and I want to automate to death everything which is going to be repeatable and repeated all the time, because it's a waste of time to spending time on this. So the strategy we followed to achieve this was, hey, we have a beautiful language in F# which has types. Like, let's use types to try to represent the process we're trying to follow or the activity we're trying to achieve. And so we automated everything we could, which doesn't change, and that will be the data loading, the learning part, the evaluation process, and make it easy to create and change features. So that was our goal, and this is how we did it. So this is actually F# code. This compiles, like this is pretty much what we did. And the core model we ended up with is this. So essentially what I did was after 3 weeks of seeing the scripts getting awful, I thought this can't go any further, I need to refactor this. And after a weekend I ended up with that. And so the model is really like this. Like I will have a type which is an observation because I have a search string and a product string, so that's fine. I'm going to define another type, which is what I'm trying to predict is a relevance. What I'm trying to produce here is a predictor, and so a predictor is a function which will take an observation and give him back a relevance. That's clear, like this is describing what I'm after. To do this, I need features, and what a feature is something where if I give you an observation, you will give me back a float, which is whatever number I care about, which is the feature I want to use in my model. And I need another notion, which is an example, because for my learning I need labeled observations, and so an example will simply be a tuple, which contains one observation and the correct relevance attached to it. And out of this, now I can define very simply a model is going to be a particular collection of features, like an array of features. I can take more, I can take less. And the learning process will be something which will take a model. So that would be like a collection of features, which will take a collection of examples to learn from, and which will give me back a predictor. One page fits on the slide, and this is like this is much closer to what it is that I was trying to achieve. The reason this was useful or interesting is like out of this, now we completely separated all the plumbing of learning and all of this from the feature extraction. And so now what I can do is I can create a file where I'm going to have a catalog of features. Instead of having them everywhere, I can write a file where I'm going to have a first feature search length. That's a feature which is going to take an observation and gives me back the length. Another one, product title length, blah, blah, blah. And I can start to create more and more and more features, and they will be centralized in one single place with the common definition. Everybody in the team can actually agree on the features and reuse them across different models. So this is pretty convenient. Because now is like, if I want to do an experiment and you want to do an experiment, I will simply create a branch. I have the same data loading code for everyone, which I can reuse. I'm going to specify what is the model I'm going to work with, and so that will be a particular collection of features. I'm going to decide on a particular predictor or learning strategy I'm going to use. So I wrote a couple of adapters for this. But so here I'm going to say, take these features, shove them into a random forest. That will give me a prediction function and evaluate it. So now this is nice because like if I look at this, like this is actually readable. I can see exactly what my model is about. Like it's not about the plumbing. It's all about like what were the features I cared about and what did I try in this experiment. In a slightly different view, so architects like diagrams, like you need diagrams with boxes. So I tried to do also a boxes diagram, a version of what we did. Is like conceptually what I try to do here is like something like this. Is like I try to separate the problem in two different sides. One side is like what is it that I will do every single time, and so that will be an experiment. So I have data which should be the same. I have the data loading part. Then what I want is I want to be able to pick up like a couple of features. I want to pick up one algorithm, so that's my experiment, and I want to shove it into the same validation process no matter what, so that everything is comparable. And on the other side, I'm building a library of things which are reusable and shared across the whole team. One of them is a collection of features, which everybody agrees on, and the other one is like a collection of algorithms we can use. And now I can say, I want to plug this one, this one, this one, put it together, run it. Is it better or is it worse? If it doesn't work, I can change it and iterate. So let me show you actually the revisited example. First, if you go to the repository, you will on GitHub, you will see that this is more or less what I showed you. It's slightly more complicated, but I didn't lie. I didn't tell you all the truth, but I tell you mostly the truth. And the way this looked in a slightly simplified way is like this. So I end up with a catalog of features. And so catalog of features is like simply a file like this one, where I see like I have search length, I have product title. So this is pretty much what I showed you, like, and I can keep building and building and building, and the team can share that. And out of this, I can now start to build experiments like this. And so I'm going to actually, I can take that experiment, and now is like I have a bit of code which is ugly here, which is like the data loading. So ignore this for a second. But the gist of my code is going to be this. Here I have a model. My model is like search length, product title, very readable. And I can say I want to now use a logistic. And I want you to validate this and check the results. And so now it's like first my code shrunk like crazy. All the boring stuff is gone. And all I have is here like features, model, and what the result was. So in this case, I can see that my predictions or my metric went down to 0.53. So this is good. And now it's like maybe I'm going to think maybe I can do better. Maybe I can add another feature. And all I would have to do for this is this. I could start to go here and say, how about using this feature? So I'm going to uncomment it. And now it's like I have a new model, I can take that model, and I can run it again, and I can see if yes or no, is this any better, and should I keep going into this direction? And it's actually barely better, but so that's the gist of what we built. So let me go back to my slides for a sec. So yeah, like the thing which was I think interesting was which is a significant difference from working with say Python or R or the dynamic languages here is like with the statically typed language, like it sometimes types get in your way, but it's an extremely powerful tool to actually represent the domain or the entities you're working with. And so here we actually used the types to model the activity we were doing, and that worked very well. And so yeah, so that's what we did. I'm going to pass on this. The question you might ask, like, did it work? I wish I was too lazy to actually produce graphics out of this, but like or bring data. But like the short answer is like it worked really well. So the history of the project was for the first 3 weeks, like we wrote scripts, and it's like it went very fast initially, and then it's like it started to go slower and slower and slower. We did this like took about like 3 days of refactoring, and after that is like we started cranking out models like crazy. Essentially, we could produce all the team produced models. We had the validation locally, and like we shipped like 2 new models to Kaggle every day, and like our rankings went up, 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 and so we were very happy, and so that worked well. So recap is like used F# types to model the domain. We built essentially a language which enabled us to speak the same language across different scripts, and we had a very clean separation in code by roles to separate features and all of this, so that we could work on the things we really care about, which is features and modeling, and not the boring stuff like loading data and all that repeatable steps. So I said like everything went well. It did for a couple of weeks, and then is like at some point, so at the point where after a refactoring, we went to the point where like we could just load data, produce a model, and have a full validation sent to Kaggle within like 2 minutes. And so that was good. It's a very fast cycle. So this is what I wanted with an agile process. Now, at some point, we started to slow down again. And so why was it? It was because we had a couple problems with the data. So I'm assuming most of you are familiar with the idea of reproducible research. So this is something which is coming from the research side. And the idea of reproducible research is along these lines, is like if I tell you that I have an awesome model which does great predictions, is like of course you will trust me because I'm a trustable person and I look honest. But if you're a good scientist, like you will say, sure, like I believe your results, but I will see the data and I should be able to run it. And if I cannot reproduce your results, I will not trust you. And so reproducible research is this idea that if I prepare an experiment or a model, I should be able to reproduce it entirely from scratch. And this is where you have another interesting difference with standard software. Like if you write a business application, usually you're not going to put your entire SQL database on version control because the data is not very important. What matters is really the code. On the machine learning side is like if I tell you I got a result of 17.3, whatever that means, it means 2 things. To reproduce this, you need the code, but you also need the data set, because without the data, like the result is meaningless. And so what you need is like you need to be able to version both the source data and the code, and you need to have a script which does the whole thing from end to end. So that's what we try to do, everything from scratch. And so that's where, and the problem is like we did that, but like that ended up slowing us down quite a bit. So, and I will explain a bit why. So I talked about algorithms and about what we're trying to do. Like the less glamorous way to describe what we did is like we spent 3 months to take 2 strings and ask the question, is this string anything like this other string? Like, is the query you gave me, does this look like what the person received? And so that sounds like a simple question until you start to dig into the data. So this is like a couple of examples of why that might go wrong. I mean, this is not really rocket science, but if I take the first query, the query and the results look similar. Like somebody wanted a ductless air conditioner, and the result was a GRE, ultra efficient, blah, 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 ductless, blah, 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 air conditioner. These 2 things look similar, except that for a human they do, for a computer they don't. Like one of them has capital letters, the other one doesn't. So I need to start normalizing the data, otherwise it will not look the same and my model will not work. Not difficult, so I can just lowercase everything like a pig, and this is all fine. Why not? So first transformation. Then a second thing, you start to look a bit into the data, and you look at, hey, like somebody wanted a 6-inch damper, and what they got was a batik door, blah, 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 6-inch backdraft damper. Again, like as a human, it's completely obvious that 6-inch is 6-inch. For the computer, like it will not look anything the same. Like inch An inch could be written as IN, could be written with very different symbols. And so this was another place where we needed to do some effort, and so we spent a lot of time recognizing that an inch is also inches, is also IN, is also this, is also that. So we had, like, again, lots of data normalization happening. And then is like other thing happen. Like, for instance, I can take another query, like 10,000 BTU window air conditioner. What came back is like a 10,000 BTU blah 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 window air conditioner. So first is like even numbers don't really look the same. You have, it's surprising how many ways you can write the same number. So here I have like 10,000 and 10,000 with a comma. In construction, as it turns out, like people will use things like 2.5, 2.5. Like, so people write also numbers in many different ways. So we had to normalize numbers. And you have another one here, as you see that somebody wanted a window air, and the result is a window air with a space. And so as it turns out, like people are just very, very bad at spelling. And so we noticed like a lot of spelling mistakes. The one which struck me the most was I thought that the word toilet was an easy one to spell. And I think we found like 16 different misspellings for toilets. And so again, like a lot of data transformations, a lot of cleanup, so that we can get into a place where we can compare strings correctly. And so as a result, we ended up with a pipeline like this. So this is again like F# code. Take a string, first transformation, fix the punctuation, fix thousands, clean units, fix. And so we went from raw data to more and more transforms. Not very difficult, but like the net result of this was we went from 2 minutes to produce a model to 20 minutes because we were doing everything from scratch. And so now I don't want to be in a place where I have to wait 20 minutes for my results to come back. So we needed to do something. First thing was pre-processing was hugely important. Like at some point, features didn't really help that much, but like all these little fixes improved the results a lot. The flip side was pre-processing is also extremely slow. And so I learned like way more about regex that I wanted to learn, but that's a story for another day. And so in a nutshell, what we wanted was like on one side, we want to keep the data intact because we want to be able to reproduce everything from scratch. On the other side is like, I don't want to wait 20 minutes. So not very difficult. We had like just 3 months. So we went from the easiest thing which could possibly work. Yeah, like first, like, so this is a quote I love. It's like in software engineering, you really have only 2 hard problems. Like the first one is cache invalidation. The other one is being willing to relocate to San Francisco. So the San Francisco part was done, but like caching is usually something you don't want to do unless you have to do. But like in this case, like we really had to do it. Otherwise, we would be way too slow. So long story short, I can talk about this more after the talk if people want, but like what we ended up doing was keeping the same pot, but having a local cache, which was essentially doing the whole pre-processing and creating a pre-processed data set locally with a hash. And so it would look like if anything changed in the pre-processing step, recompute, otherwise don't recompute. So in that case, it's like if I start from scratch, 20 minutes of computation, and then every single time it's back to 2 minutes of computation. So that brought us back to something pretty quick. Conclusion. In general, is like what I learned out of this was, I mean, in general, is like you shouldn't be religious about a process. Like Scrum is not right, Agile is not right, like whatever is not right. Is like if you want to do a process, you're doing it because you want to be productive, and so you want to look at where is it that you're wasting energy, so that you can actually make things flexible, where things are going to change a lot, and you want to automate the repeatable parts. And this is exactly what we did here. We made easy the things you actually want to spend time on, and we made it easy to change things which needed to change, and we made automated everything which we didn't care about. The other part was, so the use of F# was very helpful for us. So statically typed languages are nice because one, they give us like extremely clean scripts and extremely clean data pipelines. Like I showed you this a bit with the data processing part, is like it's very readable. And it gave us like a very clear domain model where like essentially I'm not getting runtime errors. Like the model will tell me before I even run it, does it work, does it not work? Open questions, like I don't think it's finished. The versioning we used is okay, but what I would really want is to be able to see on the version control system, I changed this feature, that feature, this feature over time. Git is great, but like it's re-versioning an entire file, and I don't have the granularity I want, which is like I want the version of the code I use. So that didn't quite work. It's not. The short version of this is like I'm not entirely happy. I'm happy with what we did, but I know it's not the end of it. And like if there are like Git beasts in the room, I would love to talk to you to see if you have ideas on this. Shameless plug before finishing. I have an awesome book. So this is what I had. So I hope you got something out of the talk. Again, my name is Brandewinder. You can find me on Twitter. If you want to talk about this, I will be very happy to talk about this. And I thank you.
Just a big